Greetings and welcome, friends. Today we're going to talk about multiplying polynomials. You may remember that the other day, yesterday maybe, in some measurements of time perhaps, we talked about multiplying and we did multiply like a polynomial by a monomial, right? But today we're going to like expand on that concept. And we're going to multiply like binomials by binomials, for instance, maybe. Like this. Not unlike this problem. In fact, exactly like this problem. Because what good is it if we only know how to multiply a monomial by a polynomial, right? So when looking at this problem, 2x plus 3 is a linear binomial, and I'm multiplying it by x minus 4, another linear binomial. There's a couple techniques we have to do this. I'm going to do what's called the distributive property first, where I'm going to take this 2x, all right, and I'm going to distribute it to both of those. Yeah, but I'm multiplying this entire set of parentheses by this other set of parentheses, right? Because you guys agree, like, if this was just 3 times a set of parentheses, we would have distributed that 3 to both of those, right?
You need to give me a reason why we're doing this.
Oh, multiplying, don't you worry. We will consider that as well in a moment. And we'll talk about the strengths and weaknesses of FOIL. So 2x times x would be 2x squared. And 2x times negative 4 would be negative 8x. All right. However, that's not the only thing that was being multiplied by x minus 4. I also have this positive 3 that needs to be multiplied. So we'll do 3 times x as well as 3 times negative 4. So 3 times x is positive 3x, and 3 times negative 4 is negative 12. And now if I want to write the answer to this, I could go through and kind of combine the like terms. Does 2x squared have any like terms in this set here?
It does not.
No, it does not.
Negative 5x.
Oh yeah, negative 8x, those guys are buddies, and positive 3x, those guys are buddies, getting along. So like negative 5x, I agree, and then negative 12 had no friends either. So this is my answer. All right, so this is called double distribution, is what I just did. I had a student a moment ago mention the idea of FOIL. Foiled it. Which FOIL stands for, if you don't know, firsts, outers, inners, lasts. All right, firsts, outers, inners, last. So by firsts, I'd be referring to multiplying the first term in each binomial. By outers, I'd be referring to multiplying the outermost terms, right? So the 2x and the negative 4. I for inner would be like the 3 and the x are the innermost terms, right? They're kind of in the middle. And then last would be the 3 and the negative 4. All right. So I like to actually, let's see if, oh, there I am. Aha. So like if I'm multiplying 2 binomials here, I'd multiply the firsts, the outers, the inners, and the lasts. You guys like that? That's pretty good. First, outer, inner, last. Good stuff. Twice is enough. You can watch this on the internet all you want later if you really want to. Just like, I don't know, maybe add some dubstep to that. That'd be pretty good. I'd be impressed. It'd be pretty sweet. So yeah. So for foiled it. Let's see. Where's my mouse at? Here we are. I'm going to multiply the first term. So 2x times x is 2x squared. Then I'd multiply the outer terms. 2x and negative 4 is negative 8x. Inner terms is 3 and x, which is 3x. And last is negative 12. And you might realize, wait a minute, this is kind of the same that I had over here. And then I would have combined like terms and ended up with exactly the same answer, which I'd hope that 2 techniques on the same problem would give me the same answer. Otherwise, one of them would come into question. But one of the things I want to point out about foiling, and why I'm not going to have this be our primary method for multiplying polynomials, is foiling only works in certain situations. All right? It only works if you're multiplying, actually, I don't think there's a part 2 to this, so I'll just write, FOIL only works when multiplying a binomial by a binomial. All right. So it's weak in that sense. I mean, sure, it's a great little way to remember this stuff, perhaps, but it only works when I happen to have a binomial times a binomial, where this distribution technique, in fact, will work for all size polynomials that I'm multiplying. And to prove that point, we'll take a look at this next little example. Example. So let's see. Example. And let's try this. Multiply the following. Actually, before we multiply this, what if we name this here? Polynomial on the left, what would I call that? It's third degree, so... No. Cubic.
Trinomial.
And 3 terms. Trinomial. So cubic trinomial, and I'm multiplying by a...
Binomial.
And what's the 2 represent for the degree?
Quadratic.
A quadratic binomial. All right? Okay, good stuff, good stuff. So let's multiply this. Multiply. So I've got 3 things this time that are being multiplied by x squared minus 9. So I'm going to have to distribute this to both of those, this to both of those, and then this to both of those. I'm kind of like triple distributing here. You know what? That's what I'm doing. Technically, with distribution, since multiplication right here is technically commutative, where I could have done it in any order, you also could backwards distribute if you wanted.
I think that'd be, it's not even, it's the same.
Yeah, it's the same thing. It's just different order. But sometimes people like distributing the fewer terms into the more terms. But it doesn't matter. But let's just do this way just to prove that to us. Let's see. So negative 5x cubed times x squared would be negative 5x to the 5th. And then negative 5x cubed times negative 9 would be negative 45x cubed, I believe. Yes, yes. Let's distribute this negative 2x now. Sign's going with it, just so you know. So negative 2x squared times x squared would be negative 2x to the 4th. And negative 2x squared times negative 9 would be negative 8. Or no. Oh, negative times a negative, friends. Positive 18x squared. And let's distribute this last one here, the positive 1. Let's see, I'll choose a slightly darker color here. So 1 times x squared is plus 1x squared, or just plus x squared. And 1 times negative 9 is minus 9. Right?
Holy smokes.
Holy smokes, maybe. Yes. So let's go through and combine like terms, if there are any.
Like terms are 18x squared and x squared.
Yeah, 5x to the 5th doesn't have any. And notice, when I go through this, I try to sort this out from highest degree to lowest degree. All right, the highest degree I saw was x to the 5th, and that's called standard form.
Negative 45 is wrong.
Yeah, that's what I was just considering for a second there.
It's positive.
Oh, negative times a negative. Oh, yeah, definitely. Man, I made that mistake twice. Well, that's why I've got you guys guarding my back. I like it.
So then you put minus 2x to the 4th?
Yeah, so x to the 4th is the next highest degree. It didn't have any friends, so minus 2x to the 4th. X cubed didn't have any friends, so that's positive 45x cubed. And then, oh wait, I think I found some like terms. Friends.
18x squared and 1x squared is going to be 19 backward. It would be second.
I agree, right? Because I add the coefficients, this little invisible 1 there with the 18, and then the exponent remains the same. So this would be my answer, which if I wanted to name this, naming by degree, it's a 5th degree, so it's technically a quintic, and it's got 5 terms, so polynomial would be the generic name for it since we didn't have a, didn't have a name for that one there. So, interesting stuff. Good stuff, friends. Good stuff. But let's, so you guys could use that technique and really just shoot to the moon with it, right? You guys would be able to distribute all the time. Good stuff, good stuff.
Maybe they have
let's take a look at this problem. We're going to end up doing this problem 2 different ways. But first of all, I want to point out the way that you would not do this problem. You would not do this problem this way. Right? Why? Because an exponent cannot be distributed over addition or subtraction. All right? But if I did want to use some sort of distributive property, what does it mean to square something?
Times it by itself.
To multiply it by itself, right? So I could actually write this out. It's multiplied by itself if I wanted to, right? And then I could just distribute this guy, right? So 3x squared times 3x squared is 9x to the 4th. And 3x squared times negative 5x squared is negative 15x to the 3rd. And then I would distribute the second term into both of those. So that'd be a negative, oh wait, negative 15x. These are like the same there, huh? Interesting. And negative 5x times negative 5x is positive 25x squared. Right? And you guys could use this technique. 9x to the 4th had no friends. Oh, but those two guys, those were actually exactly the same. Exactly the same.
Well,
So
what?
they cancel.
Do they?
No, because there's, well, yeah, because there's subtract.
No, but
Negative 15x to the 3rd minus.
Yes.
Is becoming more negative.
Yeah. You combine negative 30x cubed.
how would
Yeah.
you go about this if it was like if the actual problem was to like a 3rd or a 5th or something?
Oh, wow, that's a really good question.
Oh my goodness.
So if this was to the 3rd, then I would just have to have another set of parentheses there, right?
Yeah,
But
what if it was like,
one of the things I'd want to point out is that you cannot, all right, if I had 3 sets of polynomials being multiplied, I can't do like this as well at the same time, okay? That's not how it would work. What you would do is multiply 2 of them first, and then I would take the answer and multiply this answer by the remaining piece. So this, you'd have to do that, and that, right, and that, you know? So, so you can't like triple distribute all of those expressions simultaneously. You would have to do them kind of multiply 2 at a time, basically.
but what? Okay.
And yeah, if it was to the 5th, that would not be fun because, no thank you, right? That would just be like lots and lots of distribution. But we will actually talk about a technique in a moment about, I'm going to teach you how to deal with to the 3rd without having to do all of that work, which would be quite appreciated, perhaps. But first, this is actually a special type of problem. It's a type of pattern, and it's called the square, S-Q-U-A-R-E, I can spell, of a binomial pattern. All right, and mathematicians who are efficiently lazy people like to find shortcuts whenever possible, so they don't have to, you know, do a whole bunch of work all the time. Seriously, right? So the square of a binomial pattern looks like this. Right? Let's just look at the plus version of this first. So a plus b all squared is equal to a squared plus 2ab plus b squared. You might have seen this in Math 1 before, but
Is there a song you go
not
to?
always. No, but I imagine if there was, it would be some sort of like stadium rock song. It would be amazing. Maybe some sort of like folk ballad regarding the tale of the square of a binomial. I don't know. It'd be pretty good. But yeah, so sadly I don't have a song for this.
Can you make one up?
Maybe someday. Or maybe you could, and then just tag your video in the comments below and just like help everyone out. But this is actually a pattern we'll need to have memorized. That's right, memorized at some point. And actually there's 2 patterns in one. What's nice is if there's a minus sign here, the only thing that changes is the minus sign over there. All right, this one's always positive. And I just want to point out kind of how this makes sense. Let's look at this compared to our previous problem. Notice the first term I'm claiming comes from a squared. What's a? The first term in the binomial. So 3x squared all squared, 3 squared is 9, x squared squared is x to the fourth. So that seems to work out. Right? Same thing for the last term, the plus b squared. Right? That's just the last term in the expression squared. 5 squared is 25, x squared is x squared. So that seems to work out. Now the middle term's interesting. It's plus 2ab. Where does that 2 come from? Well, remember when I combined these like terms here, these were exactly the same. So I could have actually thought of that as plus 2 times the negative 15x cubed. All right, because there were 2 of them. And notice 2 times, that does in fact equal negative 30x cubed. So with this pattern, my oi's from the FOIL, the outsides and the insides, will always be the same. So I can just think about it as there's 2 of them. All right, is kind of where that pattern comes from. So let's do the same problem using a pattern. All right, same problem. So if I want to use this pattern on this problem, the first thing I would do is define a and b. All right, so let's actually I'll make a little using a pattern. Pattern. Here we go. Man, that's ugly writing there, but that's fine. So according to this, what part, if I'm trying to match this to this, what would the a have been?
X.
X squared.
No, the whole term in the binomial there. 3x squared would be the value of a. And what part would be the b?
Minus 5x.
Now that's where you actually have an option. I could call b negative 5x. But that would be if I was considering this as being like plus a negative 5x, all right? This pattern already has one that exists if there's a minus sign there. So if this minus sign is part of my pattern, I'll actually call b the positive 5x. All right, and I'm just going to use the negative pattern. So what I would do then is just plug all this in, the a's and the b's, into the right-hand side of this pattern. So I would have 3x squared all squared. I'm using the minus version of the pattern, so this would be a minus 2ab. So minus 2 times 3x squared times b is 5x. Plus b squared would be 5x all squared, right? So now I can simplify this. 3x squared all squared, 3 squared is 9, x squared squared is x to the fourth. This next one I can multiply these coefficients. 2 times 3 is 6 times 5 is 30. And x squared times x is x cubed. And then plus 5 squared is 25. And x squared is x squared. So I can get the answer using a pattern. Now these patterns are more important than just having an alternate route to do this problem. We'll actually use these quite frequently for the rest of this course. And in fact, for the rest of mathematics. For instance, my pre-calc kids had to go back to these patterns the last couple nights for their homework. So they keep showing up. The nice thing about it is it's always true, and you can always use it whenever you find something that's a perfect match for it. So let me give you another pattern here. This is called the sum and difference pattern. Oh, actually, you know what? Before I do that, I want to name the parts of this pattern. So the left-hand side of this is called the square of the binomial. All right, you can see that it gets its name because there's a square here and it's of a two-termed expression, also known as a binomial. The right-hand side is a little bit of a more abstract name. It's called a perfect square. All right, because these end up being the first term and the last term are both perfect squares. And the middle term actually matches in a special way too, but it's a perfect square trinomial. All right, so those names will come up a little bit later as well. Because eventually we won't only use this pattern from left to right, but we'll also be using it from right to left. So you'll have to be able to recognize either end of that pattern. Let's see, the next pattern is called the sum and difference pattern. Bow. So the sum and difference pattern, another very common and important pattern, which eventually you guys will be so familiar with this, you'll just be able to spot a sum and difference pattern a mile away. Yeah, it says that if I have two binomials being multiplied, all right, a plus b and a minus b, then it's equal to a squared minus b squared. So the left-hand side of this is called the sum and difference, all right? You could probably anticipate it's named that because I've got the sum of two numbers and then the difference of the same two numbers. All right, wow. Yeah, these mathematicians are good at naming things. The right-hand side, oh, you're going to love this name. It's called the difference of squares. All right, because there's a difference and they're both squares. Wow. Good stuff, good stuff. Now, one of the things I want to point out, this a plus b and a minus b, there's a special name when you have two binomials kind of like that. That's fine. It's fine for now. These two things are called conjugates of one another. And I believe conjugates is also a word used in English class. But the literal meaning of the word is just pairs, all right? Pairs of things, right? And conjugates, notice, are not quite the same, right? If this was a plus b and a plus b, then I could have just rewritten it as a plus b all squared. All right? If this was a minus b and a minus b, then I would have written it as a minus b all squared. But they're not quite opposites either. Because this is positive a and positive b. If these were opposites, then it would have been negative a and negative b over here. So conjugates are not quite the same. They're not quite opposites. It's just the middle sign that changes for conjugates. All right? So that's the idea there. They're definitely related because, I mean, the values of a and b are identical. It's just that sign is a little bit off. So, so let's use a pattern and do an example using this guy. Yeah, example. So let's multiply the following using a pattern. All right, and yes, I am aware that we could use FOIL on this. We could use double distribution, but we're going to use a pattern today. So 2x minus 7 and 2x plus 7. I suspect those are conjugates. How do I know? Because there's a 2x here and a 2x there. There's 7 here and there's 7 there. They're not quite the same. They're not quite opposites. It's just the middle sign that was different. So if I'm going to use this pattern, all right, the one right above here, a plus b and a minus b, what would the a have been?
2x.
2x would have been the a. And what would the b be?
7.
7, I like it. And technically, if you really wanted, you could call it negative 7, but let's save ourselves some work here. So, according to this, hey, it matches the pattern, so I'm just going to plug it into a squared minus b squared. So that means 2x squared, all squared specifically, minus b squared, 7 squared. 2x all squared would be 4x squared, minus 7 squared is 49. And the significant thing about the sum and difference pattern is that when I multiply them out, if I was to FOIL this, the middle terms, the oi in FOIL, would have canceled itself out. Because notice the outside would have given me 14x, the inside would have given me negative 14x, and they canceled out. That's why there's no middle term here. And I just end up with a binomial instead of a trinomial. Okay, so that's one of the significant things about this. One thing I might want to point out is that there's no such thing as a sum of squares pattern. A squared plus b squared cannot be reduced into the product of two polynomials like that. So let's keep cruising. I've got one last pattern to show you related to the question that our good friend El Mali asked a moment ago, which is called the cube of a binomial.
People actually watch something like they don't think that's my name.
That's fine.
People actually watch
Cube of a binomial.
That's not what I meant.
Okay, Emily, go close the window now.
No, it's still a little hot.
I'll close it in a second here. I'll close it while you guys are writing down this awesome formula.
I gotta go.
What's up? Oh yeah, you can.
Good luck at your documentation.
So, cube of a binomial pattern. Notice where the plus or minuses exist. Oh, guys, I made a mistake. What?
The formula?
In the formula. Ravioli, ravioli. Give me the formuoli. This right here was supposed to be a plus or minus sign there on the last one there. Sorry. It was just a minus sign a second ago.
Holy smokes.
So, if it's a plus b, then everything's positive. All right, because it'd be a cubed plus 3a squared b plus 3ab squared plus b cubed. If it's a minus b, the signs actually alternate from positive to negative to positive to negative. Okay, so that's kind of intriguing. But yeah, so cube of a binomial pattern. All right, and there's actually ends up being related to all sorts of stuff we'll explore later on in Math 4 and pre-calculus regarding Pascal's triangle and combinatorics and all sorts of interesting stuff pulls out of this. But cube of a binomial pattern, you can see it gets its name from the fact that it's a cube of a binomial. Wow, those guys are genius. Why didn't I think of that? So let's do one last example with the cube of a binomial pattern. Exemple, here we are. Here we are. So, cube of a binomial. So, to point out Emily's comment from earlier, I could write this as x squared minus 5x times another x squared minus 5x times another x squared minus 5x and multiply that all out. But
It says using a pattern.
yeah, specifically it says using a pattern, which by the way on a quiz, if I tell you to use one of the special patterns and you don't, I wouldn't give you any credit. Ouch. So just be aware of that. So I suspect this is a pattern. Why? Because I have a binomial cubed and I match it right up here. So if that's the case, what would A have been? What matches up with the A here?
X squared.
Yeah, the entire x squared. And what matches up with the B here?
Negative 5x.
5x or negative 5x. If you want to use negative 5x, then you would use the plus version of the formula, and you'll still get the same signs. You'll just have to do some work with negatives raised to exponent stuff. But yeah, I'm just going to call this a positive 5x and use the minus version of the pattern. So let's plug this into the pattern. So the pattern says a cubed. So I'll have a, my value for a is x squared, and it's all cubed. Now I've got the minus version of the pattern, so I'm using the minus sign here. Minus 3 times a squared. All right, so that's x squared squared times b, which is 5x. All right, we're on a roll here. Plus, because this is plus no matter which pattern I'm using, 3 times a is x squared times b squared. So that's 5x all squared. And then minus b cubed, so that's going to be minus 5x all cubed. So, good stuff, good stuff. Now I just got to go through and simplify some of this a bit. All right, so x squared cubed is x to the 6th. Let's see, this one, I'll do a couple steps of work here. How about? This is the same as negative 3 times x to the 4th times 5x. All right, because of the x squared squared. Plus this is 3 times x squared times 5 squared is 25. And x squared is x squared, of course we know. minus, ooh, does anyone know what 5 cubed is?
50.
5 squared is 25, multiplied by another 5, you get 125. And x cubed is x cubed, of course. But of course. So, all right, now I can multiply this out. X to the 6th minus 3 times 5 is 15. X to the 4th times x to the 1st is x to the 5th. Plus 3 times 25 is 75. X squared is x to the 4th. And minus 125 x cubed. And there's no like terms for me to combine, so behold, I am done. I am done. So that's how you can use some of these patterns. Work that I do want you to show is this a equals x squared, b equals 5x. Don't just tell me something like this, where sometimes people will be all like, oh, a is this, and b is that. And like that's not actually that explanatory, because sometimes people would be like, oh, the b is the 5, or the b is the negative 5, or the b is the x, or the b is the negative 5x, or the b is the 5x. And I have no idea what you're talking about. So just let's straight up, tell me like a mathematician what b is equal to, right? So don't use little arrows. So tell me your a's and b's, then you plug it in, simplify like that. All right, so thanks for watching, internet friends. Tienen un día al más bien del mundo. Bye-bye.